Is this molecule optically active? This kind of questions are asked a lot in competitive examinations, and students have difficulty understanding these questions, especially in coordination compounds, because in organic chemistry, we read about chiral carbons and optical activity a lot. But in that case, we have only tetrahedral geometry. We can have any kind of geometry in any kind of shape. This question can be asked, and you would should be well prepared to answer such questions. First of all, let's understand what optically active molecules are. So this is the experiment which illustrates what optically active molecules are. This is a source of light, and then you have light vibrating in all possible directions. So unpolarized light coming out from here, and then you have a polarizer which polarizes the plane of light, and now you have light waves vibrating in a particular direction, plane polarized light. And then this light goes into this sample of optically active molecules. And if these molecules are optically active, they will turn the plane of polarized light. So you see, it went like this and it comes out like rotated here. And then the observer can notice that there has been a certain amount of rotation in the plane of polarized light. So these are optically active molecules. And then think about these questions. You have an examination like which of the following molecule is optically active? How on earth, without doing this experiment, can we tell that which of the following molecules are optically active? I need a laboratory to do that, right? Because this is an experimental fact. Optical activity is an experimental phenomenon. No, not exactly, because logic can be applied in even those cases where you have not imagined that logic can apply. The logic is very subtle. So we are going to apply some logic here, and without doing the experiment, we can figure out which molecules are optically active or not. So I am going to think of a thought experiment which I love. It's like, suppose this there is a mirror in the laboratory where this experiment is happening, right? Then this is the mirror image world. This is the real world, and this is the virtual world. But the virtual world is as much logical as the real world, right? Even in the virtual world, whatever you see in the image, in the mirror image, is also logical, right? But you can say that that world does not exist. So I don't think that you have any right to say that this world in which we live in exists. So it's not an ontological questions. We don't have to go into this existence issue. We just have to be we just have to agree on that the virtual world is as logical as the real world, and then we can understand something about this optically active molecules. So now what happens in the virtual world is that here you see that the observer experiences x degree certain amount of clockwise rotation, but here you see that the observer is experiencing x degrees anti-clockwise rotation. So the molecules here are behaving in a different way. These molecules here are behaving in a certain way, they are rotating clockwise, and these molecules are rotating anti-clockwise. So these molecules must be different, and this is where we give a logical explanation for what is happening in this experiment. Is that the molecules here, let's say these molecules are A, and these molecules here, let's call them A prime. These are the mirror image molecules which are here, and these molecules must not be same, because if they are same, they will behave in the same way, and both of them will rotate the plane of light uh, clockwise to certain degree. But this is rotating, these molecules are rotating clockwise, and these molecules are rotating the plane of light in an anti-clockwise manner. So then you can say that optically active molecules should have a non-superimposable mirror image. So this molecule and these molecules are not same. They are not same in that terms. You can say that they are non-superimposable, right? So optically active molecules should have non-superimposable mirror image. Optically active molecules should be chiral. This is the definition of chirality. An object is chiral if it has a non-superimposable mirror image. Okay, so you don't have to look for chiral centers, chiral carbons in the molecules to think about the whole molecule to be chiral. This is a very big misconception. I clarify it here. It's very different from saying that optically active molecules will have one or more chiral centers. They might not even have a chiral center. Those chiral carbons, which you have learned in your organic chemistry, then might not even have that, because we are going to experience this topic also in coordination compounds. So you don't have to look for that. Overall, the molecule must be chiral. The whole molecule must be chiral. Okay. So let's think about this question now. Which of the following molecules will show optical activity? You see, this is a question from uh, coordination compounds chapter, because these are octahedral complexes in a way. How do we check for their optical activity? So let's take the first molecule and let's take its mirror image. And you see that the green is reflected here, this is reflected here, this is reflected here, and so on. So this is draw the correct mirror image, and then do not give up here. If you give up here, you will say that these two molecules are not superimposable, because look, the green is up there, the green is up there, the blue is down there, the blue is down there, but here we have a green, but here what we have is a blue. So this is not the same as the previous molecule. These two molecules are not similar. But wait, this is not what you have to do. You don't have to just draw the molecules, and in that, like in this drawing, it's not clear that they are same. You can rotate this molecule you can rotate and check further whether it's the same molecule or not. So what do? We can take this axis here and we can rotate the whole molecule about this axis by 90 degrees, and this green will come here, this blue will go here, that green will go there, and this blue will come here, and what you get is this. And now you see that these two are completely superimposable. So don't just draw the mirror image and say that these molecules are not superimposable. You can rotate the molecule, because in that experiment also those molecules were free to rotate and move, right? So this is not an optically active molecule because its mirror image turned out to be the same as the parent molecule. How about the second one? And this is where you don't have to even do anything to the molecule. You can see that the mirror image molecule is superimposable. How about the third one? Interesting. Doesn't this doesn't looks like superimposable on the first side, but we can do some changes. Of course, we want to bring these two on this side here. So what we are going to do now, we take this axis and rotate by 180 degrees. 180 degrees. This orange will go all the way to here. And all other atoms, all other groups will follow this 180-degree rotation. What happens now? So this green comes here, right? By 180-degree rotation here. Okay, great. So now you see that this green, this blue, this green, this blue, this whole bidentate ligand is superimposed, symmetric bidentate ligand, but these two parts are not getting superimposed. Okay, maybe we can try something else. Maybe we can this orange here, we can move this orange to that side, and this orange here we can move this to that side. So we can take this axis and rotate it. But wait a minute, when you rotate it, then this green will go down, and then again it will not be superimposable. So I think logically we have exhausted all the possibility of superimposability, and then we can say that this molecule is actually optically active, right? And you can think that this is, you can see very clearly that this is not optically active. So be careful. Thank you.